Hi everyone. Today I'm going to go over the product rule of differentiation and how to use it. As we can see at the top here, when we have a function that is a product of two functions, f of x and g of x, we write that the derivative of y with respect to x is equal to f of x multiplied by the derivative of g plus g of x multiplied by the derivative of f. And this is expressed over here using function notation, but we can write an equivalent expression using Leibniz notation, writing y as the product of u and v, where u and v are both functions of x. And if we use Leibniz notation to express the product rule, it looks like this. So dy dx is equal to u multiplied by the derivative of v plus v multiplied by the derivative of u. And so we'll call this Leibniz notation. And of course, all of this is predicated on the assumption that g prime of x and f prime of x exist. On the right-hand side here, again, I have the basic derivatives that I will take as assumed knowledge as we go over these worked examples to follow. So here, I'll just quickly highlight these two equivalent statements of the product rule of differentiation. All right, let's find the derivative of this function, y is equal to 3 multiplied by x to the power of 3/2 multiplied by 2x plus 1. So let's use f of x is equal to 3x to the power of 3/2 and g of x is equal to 2x plus 1 using function notation. Therefore, f prime of x is equal to 3, and now we're applying the power rule of differentiation. So the exponent of x comes down, 3/2 multiplied by x to the power of, now 3/2 minus 1 is equal to 1/2. Okay, so we get 9/2 multiplied by x to the power of 1/2, and g prime of x is equal to 2. Now it's fairly straightforward to put this together using the product rule. So y prime of x is equal to the first function, f of x, times the derivative of the second function, which is just 2, plus the second function, 2x plus 1, multiplied by the derivative of the first function, which we found is equal to 9/2 times x to the power of 1/2. And we could choose to simplify this a little bit. So 3 times 2 is 6 to the power of 3/2. And now let's expand the bracket around the 2x plus 1. So we get 9/2 times 2 is just 9. And then x to the power of 1 times x to the power of 1/2. We can just add the indices. So 1 plus 1/2 is 3/2. And then 1 multiplied by 9/2 times x to the power of 1/2. Now, the first two terms here with the 6 and 9 as coefficients are like terms, and we can therefore add the 6 and the 9, and we get 15x to the power of 3 halves plus 9 over 2 times x to the power of a half. And that's our answer. All right, example number 2. Let's use Leibniz notation just so we're comfortable using Leibniz and function notation. So we'll call the first function u and the second function v. So du dx is equal to 2x. dv dx, so square root symbol is the same as raising 2x minus 7 all to the power of a half. So using combination of the power rule and the chain rule, we take the 1/2 down and we raise whatever's inside this square root symbol all to the power of 1/2 minus 1, which is negative a half. And now by chain rule, multiply that by the derivative of the inside, which is just 2. And we can see that these 2's cancel. These two 2's cancel. And let's write this as 1 over 2x minus 7. All right, so we can put this together using the product rule now. So dy dx is equal to u, which is x squared plus 3, multiplied by dv dx, which we've written on the right-hand side. This is 1 over 2x minus 7 plus v, which is square root of 2x minus 7 times du dx, which is 2x. And let's try to tidy this up a little bit by writing these terms under a common denominator. So let's multiply this term on the right by 2x minus 7 over 2x minus 7. And this gives us x squared plus 3 plus, so let's bring the 2x in the front, and now we just have 2x minus 7, right? Because the square root of something times the square root of something is just that thing to the power of 1, all over our common denominator, which is square root of 2x minus 7. Now we can simplify by combining like terms in the numerator. So we have x squared here, and after expanding the brackets on the right, we get 4x squared. So x squared plus 4x squared is 5x squared. And then we have our term with a single power of x, which is minus 14x, right? 2x multiplied by negative 7, and then the constant coefficient. Right, so this is our result. As you can see with these examples, often when we're dealing with different exponents, we need to be quite careful when simplifying our expressions, because we can easily forget or make mistakes with our negative signs and our index laws. So we need to be quite rigorous with our algebra.